Hello. Let's move on to dealing with materials data, production analysis, and interpretation. Segment one. You know, people have to join for the wait for 5 minutes and then we stop. Until then, if we already those with the previous assignment, we can ask them. This is a solving session. For that channel, get this break that is the running on and I'll get a bit full. Okay, let's discuss the central planning problem. Before going into that, let's discuss some basics about the problem. Because assignment one is all about the data and the smoothing of data, analysis of variant, proper performance. In first interpretation, analysis, those things are we are going to we discussed. We have discussed in section 12, and in assignment 12 also we are going to do the same. Before that, let me introduce to what is data and why is modeling it required, all those things. So when we take a data, there are several components of it. So if you take, for example, pressure. When we plot a data, like whether it is, it will have a lot of uh, noises. This sometimes we call noises like they are like outliers from the. So these noises uh, doesn't sometimes it makes us uh, difficult to interpret the data like trend in the sense like how the progress of the y spectrum exists. For example, in this case, it looks linear, it is very clear. But if you see another case where fluctuations are like this, here we really don't know whether it is following sinusoidal or it is linear or it is like just plain kind of thing. Hence, the need for like if we smoothen this data and if we fit it, then we can see the trend better. For that only, we are doing smoothing. So trend, you have understood right? It is like how the data progresses over a bit of time with respect to its right. So that is what trend is. Long-term directionality in the data, which direction is. The cyclical. Cyclical means it is repeating patterns that occur over a time frame. For example, in my case, I have faced things like with respect to as an athlete, we do creep test. Creep test is done over strain, sustain plot, lead strain, a sustain plot. In this, in our lab, we had issues with the AC. So what will happen is like when AC is running, uh, the plot will be the curve will be going like this. Like AC switches off. Like every 12 hours, it changes. So that time the curve goes little down, and that then when AC is on, 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 like that the curve will go. So this is like cyclically this is happening at a regular interval. If you see the interval, like it is like between 8 hours, right? Like so that 8 hours can be easily identified from this. So that is cyclical. Cyclical. The repeating patterns that occur over a longer time frame. The longer time frame will be occurring over or occurring in between. So that is cyclical. Seasonal. Seasonal is a regular periodic fluctuation that occurs within a specific time frame. So if you record any data, for example, if you even record the stress strain plot, if you actually record it from the specimen using any video extensometer or a digital image correlation technique, the curve won't be as smooth like this. So actually the curve will be like, it will come like this. So these fluctuations are like the periodic fluctuations, which is because like it is from the video accelerometer or the measuring device, like in this fluctuations will occur. So that is seasonal fluctuation, seasonal compound. And then noise. Noise is a random variation. Then, for example, it may be due to the person who is like for example, if I am doing a field test, if I'm doing a website test, if someone has banged the next door, then the data might have a small fluctuation. So like that, these are like random. This doesn't have any particular reason to happen or like any particular time frame where we can say this will happen. So this is like a random, like a so this noise also has to be smoother because this doesn't represent any feature. This is merely a noise. Okay. At least we can interpret the other things with the variations because of some factors. Here it is. Here we cannot uh, correlate with any factor. This is just the random occurrence. So I hope like you would have understood the components of data. Okay, let's do a dive more deep into the what is the role of the smoothing in data analysis. So when it comes to data analysis, smoothing aims to uh, remove noise or high frequency fluctuations to reveal the underlying trends. That's now we have seen like if we have noise, it is difficult to interpret the trend of the data, where how the data is approaching or how which direction it is approaching towards, whether it is approaching sinusoidal, whether it is approaching linear, whether it is approaching the exponential. So those things has to be understood. So for that, the smoothing is essential. And then ideal process. What the ideal smoothing then refers to is it eliminates noise followed by seasonal and cyclical component to isolate the tool. So it should eliminate the variations from the noises, then seasonal and cyclical components to isolate the trend. There's some noise background.
Yeah, hello.
One second. Hello. For the interruption. So, what are the challenges which are present in this data smoothing is some smoothing technique may inadvertently remove the multiple components simultaneously. For example, it may remove the it is okay to remove the cyclical season anomalies, but if it removes the actual behavior, for example, the best example for this case is uh, if still you are aware of the yield point, yield point phenomenon, right? So it is upper and lower. So if I smoothen too much, this may become like a plastic, a normal ductile strain curve. So in that case, this yield point phenomena can be completely removed. So like the care should be taken such a way that you use this filtering technique which doesn't remove the principal component like this variation from uh, the actual curves. And difficulty in distinguishing between noise is not as I get. This is a common problem that is where it will feel difficulty in producing the distinguish between multiple components. So, things. There are two techniques for this data swapping. One is like parametric technique, the other one is non-parametric technique. The parametric technique involves like make specific assumptions about the underlying probability distribution or functional formula. For example, like if I have a data um, like this, assume it as an XRTP. So XRTP we have located the CPS converts or frequency. So here we will be having a peak like this. This peak, if we want to fit right, so it has to be compared to some function. So then only we can fit this. So for this, we can it closely resembles the Gaussian distribution and yeah, it closely resembles the Gaussian distribution. Where the frequency sharp at the end. And So in this case, what we are doing is like we are assuming a function, like Gaussian function, to fit this profile. So this is called the parametric technique, where we make a specific assumption about the underlying probability distribution or functional form. Can be a function. It's a functional function population at which the data are sampled. These assumptions often include the shape of the distribution. That's just now what we have did is shape of its just normal or exponential even like there are functions called Kelvinoid functions. All those things can possibly happen. Otherwise, this parameters that define it. Like for example, we can assume that no variance. Okay, in case of a standard of distribution, we assume the moon to be at the center and variance standard deviations same formula. Okay, so these are like parametric techniques. So let's discuss about the non-parametric technique. So non-parametric technique make minimal or no assumption about the underlying probability distribution or functional form. So this is similar to this moving average technique. All those technique they go along with the code. Like whatever the data which they get, with that they just modify the function uh, over the period of time. It doesn't make an initial assumption. Rather, it does based on the evidences, whatever it is getting in the upcoming data. So that is what a non-parametric technique is. These methods are more flexible and can be applied to a wider range of data types because like if I get a function where this uh, peak is coming and next if I get some other variation like this, if I get some other data like this together, so this can be fixed, but this cannot be fixed with the this cannot be fitted with the um, Gaussian function. So in that case, it fails. But in case of non-parametric techniques, it also accounts for the variations in this kind of variations and fits accordingly. So and in this emerging world, we have got a number of non-parametric techniques and we are continuously evolving. And whatever the artificial intelligence now currently going on, they are based on just non-parametric technique where the data, the upcoming data is like we don't know how the data is being processed. In that case, it will decide on its own. It will define. It will be modifying the function of our. So that is it's a very useful technique. So what are the several non-parametric techniques available? Data smoking we'll see. So that is moving average or rolling average is people generally call it as. This uses a specific time frame which within that it averages out the data and it gives the final output. So it is a simple method to smooth out fluctuations by averaging adjacent data points. Adjacent data points to be distributed based on the time frame which we set. Okay. So then exponential smoothing. Exponential smoothing is weighted averaging method that gives more important to the recent data. So like whatever data which is recently available based on the exponential smoothing works. Then kernel smoothing estimates the it works by analyzing the nearby data. It also gives the weights to the functions which are near the which are having high density, and it gives least weight to the functions which are away from the dense regions. So this is also weighted technique only based on the density. So next is loss. Loss is local weighted scatter cost. This is also non-parametric regression method that fits multiple regression layers to local subsets of data. There are a lot more like FFT smoothing is there. So a lot more smoothing is out there. But as a researcher, we frequently use laws, then exponential smoothing to moving and resource things. So let's see each technique one by one. Let's try to cover one exponent moving averages and kernels moving in this discussion. So other techniques, if you are interested, we can discuss further, or else we can check this out with your own techniques. Moving average. Moving average, it's like as name suggests, the average will be keep on changing with respect to the given time. So it operates by averaging set of adjacent data points for a specific window or period. It averages set of data, adjacent data points. Like adjacent data points in the like if we set a time frame like this, it averages out the data points in that time frame and it gives the output. So this is that like average. So what I have done is like I've given the deep data point to the intent language. Yeah, that's explainable is so I've taken the creep strain as creep strain as a standard, as a creep curves for this discussion of simple moving average. What we have done is, as I told you before, this is a variation that generally comes because of the repetitive cyclic variation in frequency. For a period of time, it is usually because the uh, our compressor had an issue. The temperature if we set 20 degrees Celsius, it was going to 15 degrees Celsius, close to that. And then if we set 30 degrees Celsius, it will go very close to 20 degrees Celsius. So because of this, the fluctuations were initially the fluctuation was less. Like when we set 20 degrees, it was like 19 degree, like. But after a period of time, the fluctuation started increasing. So that is the background of this fluctuation data. So what we have done is like we have tried to fit this data because like these variations are not actual features. These doesn't correspond to any microspectrum variation or any transcription deformation kind of things. So hence this has to be averaged out and this has to be developed. So for that, what we have done is like first we have imported this Greek file to the R language, which I has the Greek style and Greek time. Then we have plotted the Greek Greek data using simple moving average. First, we have plotted the whatever raw data we have got in black. So whatever you have seen the variation, it is in the black is called uh, it's a raw data. Yeah. And then what you have done is like we have drawn a line using lines and roll wheel gives the simple moving average. So as I told the alternative name for the moving average is rolling average. People call it different names, but all it represents such average mean. So simply we have used this roll wheel data frequency among time. And we have used the blue color for fitting. So we have used the uh, parameter value 5 for this. So the 5 represents the time check. So when we gave 5, it was 5. It was resulting, it was fitting to some extent, but still lot of points where like still the fluctuation was there, but then later we have increased the parameter value to 40. Then we could see like the fitting was good, but if you keep on increasing, then it will tend to be the straight line, so it don't make any sense. So hence we are to know how much we are paying to, how much not really. So that is how this moving simple moving average works. The simple representation is like if we have this is the here is just GDP per capita of Nigeria country. So if you use 3 point moving average, then it will take three data and averages out everything. So you can see like 1451, 1499, 1686. So it takes all these three and averages and gives us 1545. So next, similarly, it takes these three these three data, yeah, 150, and it averages out and gives here as 1626. And similarly, takes these three and gives average. So similar way, it generates moving average values, and if you plot, it will be like close to the without the fluctuations, it will smoothen out the plate. Another application where this moving average is used is majorly used is stock market, where for analyzing the stocks, they will be checking what is the moving average of the moving average in last 5 years or last 5 months, like that. So in this case, it is like for every month they are set to check the moving average. You can, if you simply see in last 2 years, the SES rank is going in the downtrend. So this is the moving average, which tells like the trend is downward trend. But if you see in this, if you see in this year, it's yearly path within this year only does this one. But if you see over a period of time, like from 2020, it is the upward trend. So it helps in telling like whether the stock is approaching towards the downward trend or approaching towards the upward trend. And it is easy to identify the significant changes in patterns for a period of time. Uh, and the application of that is moving and very is this kernel swapping. So kernel swapping, this takes the weighted average over the entire observed trade of this thing, where the weights are determined by kernel function. So if you want to define it more clearly, instead of just averaging the nearby values, what it does is it gives us a mathematical function to give more weights to the closer points and less weight to the farther points. For example, if I have a curve like that, okay, so more weights are given to the close arms, like the tennis ones, and least weights are given to the farther. So it provides the weights, and based on the weights, it starts to fit that curve. Okay. So what is the advantage over the previous technique? It's adaptable. So just adjust this opening based on the density of nearby points. So it can handle different patterns. So what are they? Unlike the before thing, can handle even the robust patterns and in the data. So and it does have a need and different patterns like even it has large fluctuations, it can still tell. And then no customer feasible. Like moving average, it does require they require you to give a specific window. So it is flexible and can check very detailed patterns in the data. So that one has certain advantage, like if you want to see the data in a particular time series in moving average. So when you want to show the data in particular time series, you can go for moving average. But if it is like normal data, like what you have collected experimentals, and you want to fit that, then it is best to go with the kernel folding because it works with that higher density more the weight. So let's the disadvantages on kernel folding. So that's the thing. So it's a complexity. It involves more complex mathematical calculations compared to moving average, which might be harder to grasp initially. So, involves complex mathematical calculation, unlike simple moving average, where we are just averaging out any given thing. And so, like, person who is initially understand trying to understand this, they will find it. So that's the thing. Then computational intensive computing is more than the values. These data points can be computationally expensive because it is working on this computing using a mathematical equation. So yeah, if we have large data sets, data points, then it will make it computationally intensive, since it's an expensive process compared to the previous. Generally, if you tell kernel smothering means they're mostly the Gaussian kernel smothering is being used, where the bandwidth D you can see here, right? It determines whether the profile fitting. For example, if you keep B1, so B5 means it will give you the curve like this. If you decrease the B, it will tend to become like the Gaussian profile. So, voiceover is so if they want to provide more curvature or they have to, it feels like the data variation is more, we have to decrease the bandwidth. Or else if you have, it has a smooth data or data value, means you have to go with a higher bandwidth. So, greater the bandwidth, slower the weighting changes, slower the weighting you can see. The small weights are, if it is close to zero, means we give more, we don't give more. We don't give more weight to the surface. Yeah, let's go to weight. So here is a comparison between simple moving average and kernel. As you can see here, the step fitting is in this case is given by the kernel averaging method. So because the red one corresponds to estimate and black one corresponds to estimate five. But kernel smoking gives the weight. Okay. So this is the basic theory behind whatever we are going to discuss. Have any doubt you can ask now. After that we can go with the subsequent. We go on to solve the problems. Have any doubt? move on to the problems. So which of the results does the following command get right? K smooth capital X is X and Y. X dot Y is equal to X. Kernel is equal to 1. So it generates a bit, it trims the data set X1 to fit within the box. So trim has a separate function called trim. It generates a bitter values of Y with respect to X using the box kernel average. So that is the actual thing which is happening here. It generates a bitter value. We have seen what is kernel swapping. So uh, it fixed the value of Y with respect to X. That is what it will do. So thing. Um, what are the other two options? Like generate better values with respect to it. We are given the X points as to be fixed. So hence just going to fix the X, sorry, with the value of Y, like Y with respect to X. So that's what it will do. You can see X and Y are the predictor and response variable. Predictor variables X and response variables Y. So respect to C, X dot point is set to X, which means that the conditional expectation will be estimated at the same values as a predictor metric. Very and then kernel is set to box, which means the box can be functional for those of the which generates a fertile value of Y with respect to S is box value average. But NLS belongs to the library MOS. The function calculates the NLS means non-linear least square method. So as name suggests, it produces non-linear weighted least square estimates of the parameter. So it is used to fit non-linear models to data, and minimizing the sum of the squares of the different variants are observed at predicted random. This function is particularly useful when the relationship between the variables cannot be adequately described by linear form. So wherever this linear model fails, this NLS can be helpful. And we can use NLS to compare the nonlinear model bit. Like goodness of the bit can be estimated, such as AAC or PAC, this PAC and but, uh, they determine the goodness of the bit. So you can see the syntax is NLS formula. Then the data which has to be submitted to there is start control algorithm trace what will be it. So uh, what we have done is like we have taken a data um, the time with respect to height where the height of the ball is being reached. So here when time is taken from 1 to 10 and height is taken from 2.1 to 0.8. So that is the y value which we got. And we are fitting we are going to fit the linear model using NLS, fit NLS, height in the, um, it's a formula. First we are defining the formula, height into height, A into exponential of P into time like that. Then the data is equal to data frame. Like we are taking the data from the data frame, time and height as X and Y. Then starting list from A1 to and then B starts from 0.2. So actual fitting, like we have plotted for original data. You can see it is in blue scatter plot, and then the fitted data in red lines. for getting the Nordic patterns. The library table is used in ggplot. The table is used in ggplot to not to smoothen because we have seen this techniques before that. Remove some data points is used that we use specific colors. We use colors, but colors are separate. It's in fact leaving on. But this is particular table is particularly used when drawing and insert plot within that plot. So you can see here there's a plot. Within that we are identifying to show only this region because the variation might be masked or like the variation might not be properly resolved at this scale. So we are going with a set which can clearly depict the variation, the local variation in that particular region. So for that, we can use table function to get this thing. So how to do that, I will tell you right now. So library ggplot2, the stream of ggplot. Then we are providing a sequence from 0 to 100. Then out of 1000, then it produces 1000 data. We get 0 to 100. Kind of values. Then sorry, sequential values. Then y starts from y is equal to x square is a function and generate the data for insert plot. First, we have to generate data for insert plot. For insert plot, x insert is sequence of 0 to 100 to the length of 1000, and y insert is x insert the whole square. Same function as like whatever we have written. Then we are creating a main plot. Main plot is that by ggplot plus geom aesthetics line plot. So that's why geom line plot is scatter plot. We know it is geom point will be using x is equal to x and y is equal to y. So we are defining x and y here. Then data is equal to data of plane of x, x is equal to x and y is equal to y. Then we are setting the limits from 0 to 100 for x and 0 to 1000 for the y. And labels as x and y. Also, x label as x and y labels. Then we are creating an insert plot. Insert plot is going to be plot plus same thing again, just with the x limitation from 0 to 10, with the y limit from 0 to 10. So now, enabling if you don't give outside it from the system, then you can what you have to next to do is to combine the plots. Finding the plot, final plot is plot plus annotation custom. This can be on
and what looks from where we are going to get the modulus. So, to do that, let us do the next exercise. Okay. So, here it is seen better. So, there is noise and here you can't very clearly see, but there is a little bit of noise here too. So, to do this we are going to do this exercise. Okay. So, we are going to use the library table and we are going to use library GGP miscellaneous. And so, we are going to define the main plot, which is the same stress strain curve, and we have the data that from we can have expanded. And if you zoom in, you can see that what looks like a neat straight line here actually also has lots of the it should go to the adjustment seen in our who both. Okay, now see the and you see that there is this.
No, yeah. So here we can directly combine the main block in this way, or here we can use a table to get insert block. Like if you put you define the table function. So now, like, except specify x and y values, x and y values. Here what you said x is from whether the following statement is true or false. The residual distributed randomly and QQ norms of residuals is a straight line. Then the print is bad. Okay, so generally the residuals follow. Like if you would have followed our weighted residuals from yesterday before, um, the residuals are errors which generally follow a Gaussian distribution or normal distribution. So, as we know, QP norm is to check. QP norm function is used in R to check whether the function follows the normal distribution or not. So, when we take the residual and we do QQ plot, if it is straight line, then it tells that it follows the standard normal distribution. So which means like whatever we have assumed, whatever fit we have given to the residuals is also following the standard normal distribution. So the fit is very good. But here uh, they are telling the fit is well, it's false. So, fifth question is the name of the orphan used to compute the analysis of variance is ANOVA. So, ANOVA is function which is directly given to the analysis. ANOVA is function which is used to analyze those analysis of it. And the name function which is used in R is also it's ANOVA. We have taken the three group with each 10 values. Values. And each group has it follows normal distribution, which is like it's having mean 5. Then first one follows have mean 5, second one mean 7, third one is mean 6. Then with y come to the data. What data taking your interval set that now super values are fine. Now what you're doing is like you're doing what is here use linear model to the ANOVA test. So topic of my art okay. Let's give me some time. ANOVA LM is the linear model value till their good. So they're doing ANOVA test to values in good. And the data is taken from the data, so whatever we have combined the data. So then we give predict the result, right? So we will be getting one table. So table is so here you will get degree of freedom. Uh, the first variable is value. Degree of freedom, sum. Sum of the squares, we have made the partials, we know that one is squares, and then you value and the p value. So based on the p value, uh, the decision is taken. If it is greater than the significance level, then it is failed to reject it. Say, if it is the p value is less than the significance level, it is straight away rejecting the hypothesis. So the sixth one, library FR2 for design of experiment is used for uh, it is actually the fractional factorial design. It's two levels. So we have actually discussed what is fractional factorial design. So in full factorial design, we look for all the combination. But in fractional factorial design, we rule out some factors and we give more importance to the other factors. So that's how fractionally we are doing the factorial design. So in the case, temperature and pressure would be two factors with each two levels, high and low, resulting in four possible combinations of fraction. High temperature, high pressure, high temperature, low pressure, low temperature, high pressure, low temperature, low pressure. So low temperature, high pressure, and high temperature, low pressure are unlikely to happen with another temperature, at a constant mass and volume. Pressure is decreasing, the temperature pressure is decreasing, temperature about 50. And in this case, we can roll out these two factors and we can go ahead and use the experiment. This is fractional factorial determinants and what a good function to do this. So In the case study of design of experiment induction and the process parameters like the DO was business. Induction of the shower input factors DCFR, EFR, CFR, CHR, RCL, DWR, these five fraction parameters. Fraction rate, how the CFR, total fraction outcomes. Also discussed the I1, I2, I3, I4, and I4. Or conversion application, narrow can about using the logic transformation, UI announced alpha level 0.03 that and following the logic computation from the table, action the factors, statistically showing the table. statistically insignificant is decided based on p-value. The p-value is less than 0.05. Taken for two failures. Here they have confirmed to one failure. 0.0. If the value is less than R, then it is considered as statistically. If the p-value is more than that, then it is considered as statistically insignificant. So the value for p-value is higher than 0.0. Can keep in the down to this less than 0.0. So this is not we see it for that's all it's also written BW there's more than 0.04 so we don't know that it is definitely more than 0.05. So we can consider the CFR, BW, AET, statistic lens, the logic transformation. How to find the interactive thing factors for the conversion efficiency. So, and do we do that? Factor factors for technical efficiency. Uh, what are the interaction factors? I want to I3, I4, and I5. Given in the order PFR, PFR, CFR, PFR, FR, AFR, CFR. That is order and options also. So now we have to find it out. I1 has the significance of 0.02 to I2 0.018 and I3 0.03. All I1, I2, I3 are less than the 0.0 significance level, but I4 and I5 are higher than the significant level. So statistically significant can affect the conversion efficiency is I1, I2, and I3. So in the statistical significant factors. Like the IP or attractive factors which can affect the conversion efficiency. That we are done with this assignment question. If you have any further queries, we can discuss them. you don't have any further doubts, we can conclude this session. Thank you.